in the industry, Garmire joined the University of Southern California, where she became William Hughes Professor of Electrical Engineering, Professor of Physics, and the Director of Center for Laser Studies. In 1995, after 20 years at USC, Garmire moved to Dartmouth College, where she served as the Dean of Thayer School of Engineering, author of 250 journal papers, and holder of 9 patents. She has been on the editorial board for, for her 5 technical journals. She is a member of National Academy of Engineering and the American Academy of Arts and Sciences, fellow of the IEEE, fellow of the American Physical Society, and a fellow of the Optical Society of America. She has also served on the board for other 3 professional societies. In 1994, she received the Society of Women Engineering Achievement Award. She has been a Fulbright senior lecturer and a visiting faculty member in Japan, Australia, Germany, and China. She has been chair of the NSF Advisory Committee on Engineering Technology and served as the NSF Advisory Committee on Engineering and the Air Force Science Advisory Board. Now, I would like to invite ma'am to enlighten us with a wonderful talk. Thank you.
Please, Professor,
Thank-
you can proceed now. Yeah.
Yes, yes,
Yeah,
thank you.
Madam, please kindly go ahead with your talk. You are welcome.
Yes, yes. Let me say first how pleased I am to come and give you a talk. As you see, I'm going to tell you about Raman. I'm sure you know more about Raman than I do, but I wrote my PhD thesis on the Raman effect with lasers, the stimulated Raman effect. And so I learned about Raman very early in my graduate days, and I was very interested in him. So I thought it would be fun to share some things about him with you. I also listened to the talk that you received from the religious man that came and talked to you about how to control your mind. I found that very, very interesting. I've always been interested in other ways of thinking spiritually, and I found that very interesting. So I thought I would follow his ideas and talk about the concept of creativity. I've been close enough to see it several times how creative ideas happen, and I thought it would be nice to talk about that to inspire you. I know that when I was a young faculty member, it worried me very much if I would be creative. Could I come up with any new ideas? And I was worried that I wasn't a very creative person. And it may be some of you have that same fear, and so I'm eager to talk to you about that. I also wanted to mention, I put in the corner the 3 main organizations for the photonics field. The Optical Society is one I've been very involved in. But when I first started out as a student, I was very much involved in SPIE. It gives you a wonderful chance to try out your ability to lead. And I want to tell you that I think it's very important for you to get involved with any of these 3 because, for one thing, they are all very international organizations, and it gives you a chance to experience what it's like to be in a professional society. The advantages are you can learn how to be a organizing person in a way that does not involve your job. So if you fail, there's nobody going to get rid of you. So it's a safe place to learn how to do things. It's also a chance to meet everybody else in your field and get to know other students. It'll become very important when you start wanting to find a job and having all those connections will be very important. And so certainly my involvement in all three of these societies were very important to my career. So this is why I give you the title of my talk is Raman, Towns, and You, because I want you to think about yourself and some of the things that I'm going to tell you. So Sir Raman traveled to England, you probably know this, in 1920, and he noticed the dark blue deep of the sea, and he was a very curious person, and this is the first thing that I want you to know about the creative person is that they need to be curious about the world around them. So he wanted to know, why is the color so much deeper blue than the sky? And his answer, he came up with the answer. So he postulated that it was scattering from random fluctuations of the molecules, not Rayleigh scattering, which was from individual molecules. And you may know that the sky is blue because of Rayleigh scattering. And the reason it's blue is because the wavelength dependence of the light is 1 over the wavelength to the 4th power. And so the blue scatters much more than the red, and that's why the sky looks blue. But Raman realized that that model wouldn't work. These colors are much darker than you see in the sky, and wanted to know why the colors could be so dark. And so while he was on the boat, he came up with this theory that involved using the fluctuation theory of Einstein. Einstein did everything. He invented stimulated emission, and he invented this as well. In any event, the results agreed with the things that Raman saw. So the questions we're asking is, what made Raman creative? And I'm going to just go through my feelings about this. The first thing is that he was observant. And so this is what you need to be creative also. You need to be looking for the unexpected, the unexplained. And for him, it was the color of the deep ocean. And once you observe something, I hope that you will have curiosity or wonder. You can look at the world and say, my goodness, isn't this something? I'm sure that the people that first got femtosecond pulses said, oh my goodness, how did they get that? And so there's a lot to wonder about the technology that we're working on today. And I hope that you do that. So in his case, it was, why is the sky so beautifully, the ocean so beautifully blue? And then when you think about a wonder, there are things to wonder about. I wonder why, I wonder how, I wonder if, I wonder what. And all of these things are opportunities for you to be creative. You need the questions to come first. And then related to that is curiosity. You see it, and then ideally you ask the question, why? What is this? What determines the color? And as soon as you ask that question, the next thing you need to do is ask, what do I know about this? I know the sky is blue, and I just told you that I knew that it was Rayleigh scattering, and many people, and certainly he at that time, knew that. So once you get curious, then you want to recall what you know to see if you can explain things. And this is an important point, because it means that you don't invent things out of nothing. You don't can't be creative if you don't have some knowledge to begin with. So creativity doesn't come from nothing. It comes from being curious and then thinking about the explanations that you know and wondering if they fit. So what Raman knew is that Rayleigh had explained the blue sky as scatter from individual atoms. Now, was that enough? I mean, does that answer the question? If so, there's no creativity. But the fact is that the numbers that Raman put into the equations, I mean, he sat down on his trip, he knew what it was, and he calculated the numbers, and he found much higher scattering than Rayleigh scattering would do. And the reason he realized is that water is a dense medium and you don't have individual atoms in it. So then he looked for another explanation. And again, he had done a lot of work. He studied very hard. He was a very bright man. That helps. But he really did understand a lot of things. And he went to Einstein's theory and he pulled that out and said, I think this will explain what I'm seeing. Einstein was working on a totally different problem than this. He was looking on phase transitions, but Raman was able to adapt it to his need. So he evaluated his idea. He applied Einstein's theory and compared it with experiments, and numerically it agreed very well. And what I was impressed about was that he did this all while on a ship where he had no references. He just used what he knew in his head to be able to do this. He then the next step in this process is to extend your explanation. So ideally, you can predict new features that haven't been seen before, and then you can measure them to prove it. Once you've done all that, you can publish to inspire others, and you can present your ideas at conferences, and you become famous. Brahman was very successful at that. He understood the need to publish, and that helped him a lot in his career. The rest of the story, having done all that, there are more things you need to do. If you've had a creative idea and you've come into it, what you have to do is sell your success. So the ability to explain what you've invented to other people so they realize there's something new here is part of what you have to do. And that's why we certainly expect students to be able to read and write, presumably in English, so they can interact with people worldwide. And Raman went to Cambridge with his manuscripts that he showed people. They were impressed. They invited him to come and work in their laboratories, and this was part of his becoming famous. Step 12 is to remind us that there are always going to be obstacles. It's never easy. I don't know of a case in which it's been easy. And in this, his obstacles were a physical one. His body could not take the English weather. He got quite ill, and he had to return to India. So while he might have wanted to stay in England because of all the wonderful scientists there, he really had to go back to India. And he was very determined. And the point is, if you have obstacles in what you're doing, you need to be determined to push through those obstacles until you get where you're wanting. So he set up his laboratory at the University of Calcutta, and that's where he did his work. And so the last thing, if you want to be creative and have a good career, is you really need to follow your passion. Presumably you've created this idea and now you're passionate about it. And for Raman, it was the molecular basis of light scattering, which nobody had really thought about before. Now, in your life, you're going to have to go on and do this many times. So this is, repeat the steps 1 to 10 as often as necessary. So again, be observant, wonder, curiosity, recall what you know. I think this is the same as what I just told you. Yeah, I think this is the same thing. Oh, no, I know what I was trying to do. The other thing that Raman did, besides this looking at water, scattering from water, is that when he set up his laboratories, they noticed a change in the color of the scattering light. And again, he went through the same thing. He wondered, why would the color change upon scattering? And then your curiosity, do all molecules cause color change? What do I know about this? Why should it happen? And he remembered again that Rayleigh scattering does not cause any color shift. So how do you work that out? And he realized that it must be a new kind of radiation. In fact, it's now called Raman scattering. Used to be just called the Raman effect, but now it's called Raman scattering. And what it is, as he explained it, it was an inelastic collision between photons and molecules. That was a totally new way of looking at scattering that he got out of looking at elementary particles scattering with each other. And so he then figured it out, what it meant, that the individual scattering processes are incoherent, and the intensity of the scattering depends on the density of the molecules, and therefore it really depends on the molecules. And so the change in color is because this inelastic collision meant that the collision was exciting the vibrations within the molecules. And this was incredibly important and still is today, because it's the best way to measure the frequencies in molecules. The molecular frequencies are typically in the infrared, and making measurements in the infrared are very difficult. But if you make measurements of the frequency shift from the light that's applied, it will be, it'll allow you to measure those differences. So anyway, within 2 years, he got the Nobel Prize. It's kind of interesting if you read the details of these stories, because there were 2 other men that wished they had credit. One was the one who did the problem theoretically and came to realize about 4 years before that there should be such an effect, but he didn't look for it or do anything about it. And the other person was quite simultaneous with Raman, but just a little bit after him. And Raman understood the importance of getting his work published. And so he published in an Indian journal to make sure that the date was as early as possible, because it took months to get his manuscripts sent. There were no airplanes, so it had to be sent up to England, and that took a month, and then another month to publish. So by the time it was published, it was no longer the first. But because he had reported it in India, and that was public knowledge, he got credit for being first. It's kind of an interesting story. Now I'm going to switch to something I know more about, which is Charles Townes. Charles Townes, really his invention was to invent the maser. And the maser stands for microwave amplification by stimulated emission of radiation. And you undoubtedly know that a laser stands for light amplification by stimulated emission of radiation. And stimulated emission is a process in which If you hit a atom or molecule with light, this process will induce a new photon to come out as long as the wavelength is the same as a transition within the atom. And this concept was truly revolutionary to him at that time. He had to work on the theory, and I'll tell you a little more in a minute, but here's a picture of his maser, the microwaves. You can see the microwave cavity, and you can see, I'll tell you why there's a picture of a park bench. This is a statue of him in honor of him. And the reason for the park bench is that he told everybody that he got the idea while sitting on a park bench. So we'll come back to that. But a couple more pictures. Here's him winning the Nobel Prize. And the only picture I have with him was in 2007 when we were both invited to go to a conference. In 1965, when I was doing my thesis, people just didn't take a lot of pictures. There weren't fast cameras and things. So only later did I realize I had no pictures of my lab or anything. So let me tell you a little more about the maser so you'll understand what I'm trying to get at. And what I'm going to do here is talk about invention, which is slightly different than the creativity I was talking about, the creativity which explains something you don't understand that you've seen in nature. In a successful invention, you're most successful if you can combine two different ideas together and find something new. And with the maser, Townes was able to combine quantum mechanics or atomic physics, the things he had learned as a physics professor when he was starting out. And then with World War II, he learned electronics and electrical engineering because he was helping out with microwaves and radar. And so the term quantum electronics, which we use today, comes exactly from the mixture of quantum mechanics, quantum and electronics. And as you probably have found out, it's impossible really to talk about quantum electronics all classically or all quantum mechanically. You really need a little bit of both to understand it. So the stages of invention, and at Dartmouth College, we spent a lot of time working with students to understand how to invent things. I'm going to define the various stages of the technology. And again, like with science, there is a prehistory. In other words, what is the status of technology today? If you're going to invent something new, you better understand what's going on now. And so you need to really stay up to date. So prehistory is really, it's what you know and what you can bring to the problem when you're trying to come up with something new. You also need to think about what it is you're trying to solve. Is there a problem? It could be to make a device faster, could make it smaller, make it cheaper. These all are different requirements, and they have to be, you have to know what it is you're trying to do first. Then, as I've sort of just said, what you'd like to do is have some concepts that you think are unusual and perhaps different about how you can go about inventing something new. So how can you combine ideas from two or more areas to make something novel, because you can't invent something that somebody else has already invented. So, for example, if you had something in 2 dimensions, maybe you could take it to 3 dimensions. Or there's recently been a lot of development on new ideas with meta surfaces, or meta-optics, or nanostructures produce a whole lot of new ideas. It's important to think of your invention as a system. Really, in everything an engineer does these days, they're working in somewhat more complicated systems or devices. So you can take whatever concept you're talking about here and divide it into separate parts that you then are going to combine to make a system that's presumably going to work. And as you're working on whether or not this will work, you need to specify each part and what its performance will be. And again, this depends on previous experiments and theories that either you've done or that you have read in the literature about, so that you know what it is you want to combine. I'll show you in a few minutes that for the first lasers, a laser needs a medium that can be inverted population to get stimulated emission. It needs a pump source to make that happen. It needs mirrors to be able to provide feedback. And those are three main parts of a laser. And sure enough, Townes in his first experiments worked exactly on that concept of making sure he had all the parts before he actually built it. So once you've got the system defined, you can then analyze it, see how the parts combine in a new way to produce some kind of a viable new result. And from that, you would design a prototype. The prototype is really a preliminary model from which you can develop an optimized system. It's certainly not the final model, and this was certainly true in the lasers, and again, I'll go through that. And ideally, you will submit a patent application. If your work is being paid for by the university or by industry, they will expect you to submit an application for a patent. And in case you don't know it, getting a patent does not require building the device. It only requires that it could be built. And if somebody decides it can't be built, you can't get a patent. For example, if you invented something that was perpetual motion, they would be rejected for a patent because we can't have perpetual motion. So who gets the patent is the first to claim the invention. So the time frame is very important on this. And to get the invention, you need to be able to publicly declare through talking or publishing before anybody else declares the idea. And then you build it and you fund it or get someone to fund it. And this always takes time. And then if you've got it successful, you sell it and you become rich. And I put a maybe in there because that doesn't always happen. In fact, there's Lise, in is the slip between the cup and the lip. Or we talk about the valley of death in startups when before you can get enough funding to really build your startup into a company, it's hard to get through that unless you get funding, and so that's where most companies die. And in the USA, only about 1/10 of all startups become profitable. It's an exciting thing to do, and a lot of people do it, but you have to do it knowing that you're not guaranteed by any means. So typically people will have an alternative plan. In the US, many people remain employed and start the companies on the side. And this is particularly true of professors like Townes. So he followed the pattern I just described. He was an atomic physicist. His study was molecular spectroscopy, and he learned about microwaves during World War II. And through his research into radar. He also learned about microwave cavity technology and electronic oscillators from the electrical engineering that he was doing. As an atomic physicist, he knew about stimulated emission, and he realized that stimulated emission produced gain. And he knew and gain, of course, is an engineering term, and he knew that if gain was greater than any loss that you have in the system, and you have feedback, that if this condition is true, the device will oscillate. And electrical engineers knew that because they would build electrical amplifiers that would suddenly start oscillating. So he sat on a park bench, the one I just showed you, to calculate out what we call a back of the envelope calculation. So here's an envelope, and you can see the calculations that people do when they don't have anything else to write on. And so he calculated the gain from ammonia vapor, and he calculated how much feedback he could get from a microwave cavity, and he discovered that he should be able to create an oscillator. And so the maser really, what he really wanted to do is to make a true oscillator, because if it's an oscillator, what you're doing is creating a new frequency where that frequency never existed before. And so the ammonia vapor was at 1.4 gigahertz. And yes, it worked. He became famous and got the Nobel Prize. So I wanted to tell you a little bit about lasers, just because, again, that's my field. It's also makes the points I've been trying to make. As we mentioned, we got towns made the laser work in 1953, and the ammonia beam is not a very practical thing to have as an electronic piece of equipment. And it was 3 years later that it was predicted that a ruby could make a maser, and that was successful in 1958. And so ruby was a crystal that was being used regularly for masers. Also at this time, there were flash lamps available, and also low temperature dewars. So if you want to build a system, you need these sort of things available. That's the technology that went into the first laser. Now in 1958, the laser was theoretically predicted by Townsend Shallow. They were able to do the same thing he did for the maser, to predict exactly what gain you would need and what feedback you'd need for an optical maser. And that was published and so in the open literature, and they predicted, their calculation was on some strange potassium vapor laser which never really worked, but the competition began to find something that would work. So we're now reaching, as far as the laser is concerned, the invention stage. And here we have several lessons that we can learn. Whoops, I did that. That was a mistake. Hold on. There we go. One of the things that we can learn is that the first laser was a ruby, and Maimon, the person that did this, had been working with a ruby maser, so he knew all about ruby. And so he thought about using a ruby. He put the numbers into Townsend's equations and thought it would work, but he needed a huge amount of light to optically pump it. So these flash lamps had been invented during the Second World War for illuminating the fields at night so that photography could take pictures of during war. And so he had the idea, let's put a ruby inside of here and that'll provide the optical pumping. Well, he needed mirrors. He just polished the two ends of the ruby and put silver on them. So it was a very simple design, and he could pulse these lamps with as much power as he wanted, and they were very bright, so he got a huge intensity of light coming out, and it was invisible. So it was if you did it right, which was 77 degrees Kelvin, if you put it in a dewar, you could get vast amounts of light coming out with a very low efficiency, a 4% efficiency. And it was visible as pulses. You might ask why Bell Labs, who already knew about the laser, hadn't been able to build one. The reason is that they wanted to have, I'm sorry, okay, they wanted to have a continuous laser. They were planning to send telephone calls down these light beams, and they knew that it would have to be a continuous laser for that. And so they didn't like the idea of pulses at all, so they didn't try that. In fact, they were shocked when Raman beat them to their first laser. Now, I'm going to tell you what happened in the first 5 years after that laser was invented, because there were new lasers. Everybody just immediately worked hard to be able to come up with a different laser. The first laser that somebody else came up with, well, just for fun, let me give you these dates. This was in May, the first laser. By November, that's only a few months later, at IBM, they completely copied the Ruby design, complete with the dewar and flash lamp and everything, in uranium calcium fluoride, which they happened to be working on, and it worked, but it was of no value. Nobody ever paid attention to it because it was very inefficient and it wasn't a useful laser. On the other hand, within the month, Bell Labs finally got their laser to work, and it was a gas discharge of helium and neon. And it had the advantage of working in room temperature and, again, not very efficient. It put out a low power infrared beam at that time. Another laser that happened a year later was a neodymium doped glass. And what's interesting about that is that, in fact, they were in fibers, and American Optical was a company that was working on fibers, so it was easy for them to make them. It worked at room temperature, it worked continuously, and it also had a lamp, but a continuous lamp. And look at that efficiency. It was 70% efficient. You'd think everybody would jump into working on that. They didn't, because I guess they were impressed that the power was at a continuous basis. The power was pretty low, and people were getting all excited about the Ruby. A year later, the first gallium arsenide diode laser was invented, and I'm going to talk more about that. 2 years later was the ionized argon. The argon laser was a very energetic discharge that took a lot of power, quite inefficient, very inefficient, but it's the first time they got blue or UV and many watts of continuous light. So the argon laser is still used occasionally. It was very important for probably 40 years. And I can tell you that the first time I saw one, it blew my mind. It was so beautiful. At about the same time, Bell Labs also invented a crystal laser, neodymium doped in YAG. YAG is yttrium aluminum garnet. And these were very efficient IR emitters. They can be as much as 70% efficient if you do them right. And again, the same time, the carbon dioxide was another discharge laser. It was very highly efficient. Its problem was it operates at 10 microns, but it puts out many watts, enough to heat all kinds of things. So it's used for machining and heat treating of metals. And the other one, dye laser, which with liquid, they dissolve the dyes into liquids and they pumped it with another laser. That was the optical pumping. And it had the big advantage that it was broadly tunable because nothing else was tunable. And so this was important. And look down and see how some of these really aren't used all that much anymore. On the other hand, replaced by the second harmonic of the which can put up the same